Okay, so basically this is what a pulley looks like. It's a metal object for assisting in lifting heavy objects. Okay, so you can have situations, you can have systems with one pulley, you can have systems with multiple pulleys. So I think if you do physics, you may learn that if you have multiple pulleys, then you need less force to lift up the object. So obviously there's going to be tension in the string, tension here. Okay, but in the second situation, if you have more pulleys, then the tension in the second case is going to be less. That's the kind of things they do in physics. So in chapter 10, the kind of pulleys you'll be looking at are smooth pulleys. So a smooth pulley means there is no friction in the pulley. Okay, so that means that the tension on either side is going to be the same. Okay, so the pulley is applying a force to the person. So there's a tension here, but the person is pulling. The person is pulling against the pulley, so the person is applying a force to the pulley. So there is tension here as well. So that's the kind of modeling things you're going to be doing. Okay, going to go through the examples. So got two particles P and Q, mass 2m, mass 3m, attached to the ends of a light inextensible pulley. So I need a drawing really. The string passes over a smooth pulley. So the question is about a pulley. So I'm going to draw a pulley. The string passes over the pulley. So this is that was supposed to be the string. This is the other end of the string. Okay, there are two masses on the string, particle P, particle Q. One has mass 2m. The other has mass 3m. So this is particle P, this is particle Q. Okay, so first thing, these are the masses, so that means they're going to have a weight. To work out the weight, you times by G. So this is the force on the 2m mass, 2mg. This is the weight of the 3m mass, 3mg. So the 2m particle P, the 2m mass is connected with the pulley. So the pulley will apply a force. So the pulley will exert a force on the 2m mass. That's the tension. Newton's third law says there's an equal and opposite force. So the 2m mass will apply an equal and opposite force on the pulley. Okay, so that's how you set it up. Okay, then you do the same thing with the 3m mass. The pulley is connected to the 3m mass. Okay, so the pulley is exerting a force on the 3m mass. And also the 3m mass Q is applying a force on the pulley. Et. Okay, so all these tensions are the same because we're told it's a smooth pulley. So because it's a smooth pulley, all the tensions throughout the string are going to be the same. Okay, so those are the forces. The system is released from rest. So the heavier object will go down. So 3m mass must go down. Acceleration. And the 2m mass must go up. They're connected by the same value. So that is the situation. Okay, so what do you need to do? Okay, so you want to find the equation of motion for each particle. So the equation of motion means you just need to apply F equals ma to each particle separately. So for A1, okay, if we look at particle P, so particle P is moving upwards. Okay, so the resultant force, there are two forces on particle P, T and 2mg. Motion is upwards, so the resultant force on particle P will be T minus 2mg. And that is equal to the mass times acceleration. So remember, equation of motion, I need to do resultant force equals mass times acceleration for each particle separately. So that's what I'm doing. T minus 2mg is equal to the mass, which is 2m, times by A, which we don't know. Then we do the same thing to particle Q. Particle Q is moving downwards, so the resultant force will be 3mg take away T, because it's moving downwards, so it's the other way around. The resultant force equals the mass of Q is 3m, acceleration is the same, known. So those are your two equations of motions for particle P and Q. Okay, part B, to find the acceleration, you need to solve the equations. So to answer part B and C, you solve those simultaneous equations. So the easy way to do it is just to add. If you add the equations, these will cancel out. Minus 2mg plus 3mg is just mg. 2ma plus 3ma is 5ma. So look, the m's cancel out. So the acceleration is g over 5. So you can leave your answer in terms of g. Okay. If you want to work it out as a calculator, on a calculator, it's about 2.0. We round it, 2.0 meters per second squared. So that's the exact value, g over 5. Any questions on how I got the equations? How I solved to find A? To find the tension, I just need to substitute and solve. To find the tension, you can use either equation. So you can say, okay, so from the first equation, T is equal to 2mg plus 2ma. But we know what A is now, g over 5. So if you add those together, you get 12/5 mg. 12 over 5 mg. Okay, so that's the tension. Okay, part D. Find the force exerted on the pulley by the string. Forces on the pulley. Okay, so from my diagram, my pulley only has two forces acting on it. T plus T. So to answer part D, the force on the pulley is just T plus T. So it's just 2 times 12 mg over 5, which is equal to 24 over 5 mg. That is the force on the pulley, T plus T. Part E, find the distance. So it sounds like a Suvat situation. Okay, so for part E, find the distance moved by Q in the first 4 seconds, assuming P does not reach the pulley. Okay, so particle P, you want to find out what S is. You know, T is 4. Remember, the whole thing starts from rest. The system is released from rest. So U equals 0. Okay, so we need a Suvat equation to find S. So we just use S equals UT. That's half AT squared. Because we know what A is, don't we? We also know, remember, that A, we already worked out, is G over 5. Okay, so we can use the equation S equals UT plus half AT squared. Okay, so plug in the numbers. U times that will just give you 0. Half times. Okay, so the value of G we can use now. 9.8 over 5 times by T squared, 4 squared. So you work that out on a calculator to get 15.7. So particle P will fall 15.7 meters in 4 seconds. And the last part, how have I used the fact that the pulley is smooth? If the pulley is smooth, it just means the tensions throughout the string are the same. Part F, smooth pulley, tension is same throughout the string. Last example, example 14. Okay, this involves a table. Two particles A and B, 0.4 kilos, light inextensible string, lie on a rough horizontal table. A lies on a table, rough table. There's a smooth pulley, which is fixed at the edge of the table. Okay, so I'm going to draw a table. There's a pulley on the end of the table. String will pass over it. Okay, I have particle A is lying on the table. Particle A. So this is connected to the pulley. Okay, this is the rest of the table. Okay. The string passes over the pulley. And you have another mass B hanging over. Okay, so forces, so the mass of particle B is 0.8 kilos. So there is a force of 0.8 G newtons on particle B. Okay, then it's the usual thing. This is connected to the pulley, so the tension is the same. Smooth pulley, ET. Same situation here. Particle A is connected to the pulley, tension on the particle A, tension on the pulley, TT. Tension is the same throughout on a smooth pulley. What else you're told? Particle A is 4.5 meters from the pulley. The string passes over B. String is taut. B is 0.5 meters above the ground. Okay. Frictional force of magnitude opposes particle A. So particle A has a frictional force. So there is a force on particle A, 0.08 G. That is a frictional force. It makes sense because it's a rough table. And you're told the system is released from rest. So if the system is released from rest, hopefully you can see that it has to move to the right. So this is going to move down, unknown acceleration, and this is going to move to the right with the same acceleration. So they're connected. So that is your situation. In the book, they've put in the force, they've put in the vertical forces on A. So obviously you've got 0.4 G, the weight, and you have the normal reaction. They've done that in the book, but you don't need it to answer this question. Okay, so you need to find acceleration of the system. So you need to do F equals ma on them separately. You can't do F equals ma on the whole system because they're not moving in the same direction. They're moving in opposite, they're moving in different directions. So you need to do F equals ma, find the equations of motion on them separately. Okay, so if I look at particle A first, I want to do F equals ma. Resultant force equals mass times acceleration. So particle A is moving to the right. There are two forces, T and 0.08 G. So the resultant force is going to be T minus 0.08 G. That is equal to its mass, which is 0.4 kilos times by A. So that gives you an equation with two unknowns. You do the same thing again, but we do particle B. So you're going to do F equals ma. So the particle B is moving downwards. So the resultant force will be its weight, take away the tension on B, equals the mass times A, 0.8 A. So those are your two equations. So you need to find A. So if you add the equations again, you can cancel the T. So to find the acceleration, you add the equations to cancel out the T's. So when you add them together, 0.8 g minus 0.08 g is 0.72 g equals 1.2 A. Divide both sides by 1.2, you'll get A to be equal to 0.6 g. So that's the acceleration in terms of g. So you can leave it as an exact value, or if you really want to, you can do it as a decimal, but you may need the exact value for the rest of the question. It's good to make a note of 0.6 g. That's too sig fig. That's the acceleration. Any questions on that? So similar to the first example, but one is moving to the right and one is moving down. Next bit sounds like SUVAT. Time taken to reach the ground for particle B. So now you've got to think about some kind of SUVAT for particle B. So for particle B, remember you're told it's particle B is 0.5 meters above the ground. S equals 0.5. You want to find the time taken. We know the acceleration, we just worked it out, is 0.6 g. And the whole system is released from rest. So we know U is 0. So you can use S equals UT half AT squared again. Okay, so we have 0.5. U is 0. That term is 0. Then it's half AT squared. So it's going to be half times by 0.6 g. So I'm going to put g is 9.8 times by t squared. So if you do that calculation, you'll get the time. So it's about 0.41. If you solve that equation, 0.41. So from here, if you solve that equation, we'll get t equals 0.41. seconds. Okay, any questions on part B? Part C is the tricky part. Find the total distance traveled by A before it comes to rest. Okay, so in the question, so as the string is moving, as the particles are moving, the string is taut. Okay, that phrase means there is tension in the string. So when you talk about a string which is taut, that means there is tension in the string. So when there's tension in the string, the particles are connected. So you want to find the distance, the total distance moved by A before it comes to rest. Okay, so when they're connected, when particle B hits the floor, the particle B will travel 0.5 meters to hit the ground. So that means particle A will also move 0.5 meters. So as long as the particles are connected, particle A, so when particle B has reached the ground, 0.5 meters, particle A must have traveled also 0.5 meters because they're connected particles. So the first part, the total distance, so initially when the string is taut, so when the string is taut, so taut string, when there's tension in the string, A travels 0.5 meters, the same as particle B. That's when the string is taut, okay? But when particle B hits the ground, then there is no tension in the string. So the string will become slack. So what happens is that particle B will still move, but it will only move a little bit, and then it will stop. So that's what you need to figure out, how much it moves when the string becomes slack. That's what you're trying to figure out. So the idea is that as B hits the floor, the string becomes slack. So this is the opposite of taut. Okay. String becomes slack. In other words, T becomes 0. So that means particle A will have a new acceleration, which you can calculate. So I might as well do that now. So if we look at the equation over here, that was the original equation for particle A. Okay, so now if I put T equal to 0 here, replace that with 0, T equals 0. So when T equals 0, that will give me a new acceleration, minus 0.08 g equals 0.4. Okay, I need to use a different letter. In the book, they use A dash for the new acceleration. So I'm going to use star. Okay, so A star is the new acceleration of particle A when the string becomes slack. So if you do that calculation, okay, so if you work out minus 0.08 times by 9.8 divided by 0.4, you'll get minus 0.02 g. So that tells you particle A is decelerating. So particle A is becoming slower and slower and slower until eventually it will stop. So eventually particle A will have velocity equal to 0. So we want to know how far it moves until it stops. So we need to figure out from the situation what the U value is. So what is the speed of A when it starts to decelerate? Okay, so the speed of A, so when the string becomes slack, the speed of A will be exactly the same as the speed of B when it hits the ground. And that's the idea. So the speed of A when the string becomes slack will be exactly the same as the speed of B when B hits the ground, which is something you can work out. So you work out the speed of B as it hits the ground using a suvat. So you can use V equals U plus AT, I believe. So for particle B, if you use V equals U plus AT, find the velocity when it hits the ground. Okay, so the velocity when it hits the ground. Okay, so remember it started from rest. The acceleration of particle B when it's moving is 0.6 g. And the time taken to reach the ground, we already worked out from part B, 0.41. Okay, so in the book, they use the more exact value. So it's probably not a good idea to use 0.41, that's the rounded value. So in the book, they've used 0.412, so they've used more digits basically. 0.412. Okay, so they've been more precise. And that gives you the speed of B as it hits the ground. So So I've used the symbol VB. That's the final velocity of B as it hits the ground. So again, they've put in extra digits to be precise. So that's not the final, this is just part of the working. So that's the speed of B on the ground. Okay, but that speed must be the same speed as A when the string becomes slack. So we can use that as the U value for A, particle A. So we can use that number, U equals 2.424, etc. .424. So we can use that value as the initial velocity of A when it begins the second part of the motion. Okay, so now you can use a suvat to work out how far it travels. So you're going to use v squared u squared 2as. So for this last part, I'm going to use v squared equals u squared. Okay, so when particle A will eventually become 0, slow down, so it stops. Okay, so we know this is going to be u squared, so you need to work out 2.42 exact value squared plus 2as, so that's going to be, yeah, you need to use those numbers, minus 2 times the new acceleration, which is a deceleration, 2 times 0.2 gs. So that gives you an equation to find s for the second part of the motion of A. So if you solve that, you get about 1.5 meters. So if you solve that equation, you get s to be 1.5. Okay, so that's how far it moves when the string becomes slack. But the question is asking you for the total distance moved by A. So remember, when the string was taut, it moved 0.5 meters because the particles were connected. So to answer the question, the total distance moved by A will be 0.5 plus 1.5. So the total distance moved by A, so the total distance is going to be equal to 0.5 meters plus 1.5, which is 2 meters approximately.